So it is my pleasure to introduce Professor Mohammed Kutbi. He's an assistant professor at the Department of Computer Science and member of the Artificial Intelligence Unit at Saudi Electronic University. His research interests lie in the broad areas of computer vision and robotics. His recent work includes motion segmentation, domain adaptation, and human-robot interaction. He received his master and PhD from the Department of Computer Science at Stevens Institute of Technology and his bachelor from the Department of Information Technology at King Abdulaziz University. Today, he will talk about an egocentric wearable camera for assistive technologies. So please, Professor, you can start.
Okay, thank you so much for the introduction. And thank you for the invitation for the organizers. Also, thank you for the attendees for showing interest and being here. Thank you. Today I'll be talking about a project I've been worked on for 4 years during my PhD and after. And I'll also introduce some part of my students' senior projects as well at the end of this talk, inshallah. So the title of this talk would be an egocentric wearable camera for assistive technologies and specifically wheelchair. So the outline will be, first we'll introduce a hands-free robotic wheelchair. Then we will show several applications for this hands-free robotic wheelchair design. Then we will show cases for ways to learn from users driving the wheelchairs. So learning how to navigate based on users' experience. Then last we will talk about a guide for people with sight difficulties and how a wearable camera could assist them in navigation. First, we'd like to start with the motivations for why wheelchairs are important, why we're interested in developing technologies for wheelchairs. First, we would like to something very nice to improve the quality of life for people or wheelchair users. And some statistics regarding wheelchairs users are estimated number of 1% of the whole world population are in need of wheelchairs, regardless if they have access to one. In the United States alone, there's 3.6 million users of wheelchairs, and more than 100,000 injuries a year caused by wheelchairs navigation. In Europe, there's 5 million wheelchair users, with 2 million of them suffer from reduced upper limb mobility. And those people we're targeting, people who suffer from upper limb mobility and they need other alternatives other than joysticks to navigate wheelchairs. About 10% of users also require some sort of help to use their manually controlled wheelchair needs, and more than 40% of users have difficulty steering and maneuvering tasks. And these are the tasks where you will have to do in narrow areas, areas in homes, in corridors, or where it's very hard to navigate, especially for those wheelchair users who suffer from mobility in the first place. So they may actually suffer from other difficulties. We're not the first to do this, to develop hands-free robotic wheelchairs. There's multiple methods that's been proposed, and some of them are related to voice recognition commands, where the user will say a couple of words saying move forward, move backward, turn right, turn left, and then the wheelchair will navigate. Some will be related, such as this one to the right. We will see chain control, where the user will put the chain on a joystick and then applying some force to the joystick will allow them to navigate. On the other side, on the left side here, there's a sip and puff, where you could control the wheelchair using the way of breathing. Depends on how you breathe, then you can drive the wheelchair. Also in the middle here, you can see some ECG and EEG, AOG technologies, where you have a helmet that has some sort of sensors and it picks different types of signals. And analyzing these signals will allow us to communicate with the users using their electronic signals they produce. Also on the computer vision side, there is gaze and facial detection, gesture detection. That's also a method that's been proposed, where you have a camera looking onward on the user, and based on their eyes movement, you can navigate the wheelchairs. However, overall, these methods suffer from one or more disadvantages. One of them is that it requires a physical force towards the joystick, such as the chin-based control. It requires some physical force that may cause injuries on the long term, or such as the EEG ones. They may require a lot of calibration per user. So you'll have a user coming in, and then you have to learn how the brain signals are sent, and then you'll have to train them into certain thinking, a certain way of navigating the wheelchairs. So we looked into avoiding a lot of calibration, avoiding applying any physical strain on the users. And the third one is allowing continuous directional control, not only going backward or forward or right or left. We want to have omnidirectional control, where you could go 306 different orientations and multiple levels of speed. If you think of the voice control command, there's one speed. You can say go forward or go back, but you cannot say go 3 degrees to the right or 4 degrees to the left. It gets a little more difficult. So that's where we designed our method towards. Also, when we thought of the design, we also thought of having affordable equipments. We did not look to have very expensive sensors or devices. The equipments we used is comprised of simple wheelchairs that we hacked this joystick, and we replaced it by a microcontroller. And then we connected it to a laptop for processing. We have a Connect, of course, for SLAM and navigation, for mapping and localization. And then we have the tablet in front of the user for feedback. So the user will be communicating with the system, and we will get some feedback, allowing them to interact better and drive the wheelchairs smoothly. Also, what's important to us and most important part is the egocentric camera, or the wearable camera. So the user will wear this hat with the camera, allowing them to share the point of view and allow him or her to drive the wheelchair based on it. So how do we get the more communication between the user and the system? The head pose we developed a method to calculate the head pose of the user. So simply relying on two components, relying on the head mounted camera and the QR marker mounted on the tablet. So based on wherever you see the QR marker, then you can calculate where the person is looking. As long as, of course, the QR marker is in the field of view of the camera. And based on that, we actually move a cursor on a tablet. So the tablet in front of the user has a cursor, such as this one. And this cursor moves as the person moves his head or her head. And then, so the user can feel the feedback coming back from the system and knows if it's picking up his commands or not. Now, the simplest interface we developed is a simple one button to the left. And then using these buttons, if you move the cursor on these buttons for 3 continuous seconds, and then you enable the navigation mode. A virtual joystick will be shown up on the system. And this virtual joystick, you can pick it up the same if you move the cursor to the joystick continuous 3 seconds, and then you will pick up the joystick. And then simply moving the head will allow you to move the cursor again, and then you can start navigating. Now this simulates a higher speed or maximum speed moving forward. If I want to go to the left with a lower speed, then I get closer to the center. If I want to go backward, then we have the backward camera showing you the field of view in the back of the wheelchair, which allows you to better, similar to what's in a lot of cars right now. Then to disable the navigation mode, you put back the joystick in the center, leave it for 3 seconds, you disable navigation mode, and we exit. I'll show a quick clip for how this method works. As you can see, it's a simple head motion. It does not apply any physical strain on the neck or any part of the user's body or the wheelchair user's body. as it turns, you can see part of the interface. Okay, so to show the importance of having a continuous directional control, we decided to run an experiment. We recruited 10 subjects and we designed a navigation mode for them and we asked them to navigate from point A to point B, but twice. Once using our navigation mode with the full directional control, full speed control, and then the other way where we had a fixed speed, which is the maximum speed, and we fixed the directions. We said there's only 4 directions you can go, either forward, backward, right, and left. And we wanted to see whether having omnidirectional or continuous directional control makes much of a difference. So this was the view of the task we asked the user to do. We have a from start point to the end point, and these are the boxes showing here. We ask the user just to navigate through them and get to the end point. Of course, as we anticipated, that the continuous directional control, on average, users finished in 88 seconds, comparing to 219 seconds for users who use the for discrete control for the same users. And to avoid any biases, sometimes we let the users, half the users, we allow them to start with the continuous directional control, and half of them we ask them to start with the discrete first and then the continuous. In regard to also the questionnaires, we ask them whether they felt more safe, whether they felt more comfortable. And it's noticeably that in all questions, users who thought the continuous directional control had a better sense of feeling and comfortability in comparison to a discrete directional control. On conclusion on this method, this method provides 4 things. It provides continuous directional control of orientation and speed. It has the advantage of having affordable sensors. Webcam is very cheap. A tablet, nothing that's actually very expensive. No expensive sensors. Minimal physical pressure, or almost no physical pressure on the users. It requires no calibration free. For all the 10 users, 10 subjects we recruited, we didn't do any calibration, so they all use the same one set of calibration for everybody. And then last, when thinking of the egocentric camera or the wearable camera, it extends the field of view of the robot. So if we think of the camera mounted on the robot, on the robots here, the field of view is fixed because it does not change to right or left. However, the camera on the user's, the wearable camera could change. So its field of view keeps changing as the user moves their head right and left, which could give us more information, allow the system to have more information to work with. So this is one of the things. Second is it shares the field of view of the user, which allows it to serve as a mean of interaction. It allows us to, we'll show now in some of our applications, how do we take advantage of the wearable camera to serve as a mean of interaction to the system. There's 4 applications we decided. First, we simulated a home navigation. We created a studio. We said on different areas or different parts, we predefined the map. And we integrated some voice control commands beside the hands-free control. And then we show on the tablet the map and the path for the users. And it was a semi-autonomous navigation. How is it semi-autonomous? We allow in this path in home navigation, we design it to be used in a home environment where the user will be saying, I want to go to the bathroom, I want to go to the bedroom, I want to go to the kitchen. And then based on what they say, we allow them to go. The semi-autonomous part comes in where we ask them, at the time we're not certain on which path should we take. Let's say I have a big home, I have multiple routes to take to get to the same destination. Not always the shortest path is the most preferable path. The user may have their own criteria. They prefer to go from certain way or certain road. And this also happens in cars driving. Drivers now sometimes not always take the shortest path, but they take the path they think is the best. based on maybe less hazard, maybe less traffic, or many other criteria that's not recognizable, or it's not easily recognizable by programs. So in this scenario, we thought of it as a path selections situation. We allow the user to choose which route they want to take. And then based on that, we will show how we learn from the users. For now, let me show you just a scenario of what I mean by home navigation and what's coupled with the uncertainty model. When the system is not certain, then it asks the user for a direction. The user now asks the system to go to the bedroom, and then it shows multiple routes on the screen, and it asks which routes would you want to take. Would you want from the right or the left? The user chose right, and then it took the user easily to the destination. Try to speed it up. Then the user picks study, and then because this time was certain, there's no other path, so it did not ask for more information. In the first time, no, there were multiple routes, similar in distance, so it thought maybe I should ask the assistant. Second time, there was no really valid alternative. It was only this way. It could go from behind this. So actually, there was two ways. It could go from behind the table and come all the way, but it wasn't an option that's very pleasant or likely the user will pick based on user previous destinations. It comes back all the way, comes to the center. The second application is where we thought of it as if it's you're in a conference and it's a poster session where you have multiple posters around, and you want to go as a wheelchair user, you want to go from poster 1 to poster 2, you want to go to a certain poster, you want to get closer to it so you can read it, or you ask the authors, etc. When we did the same setting, we have two cameras. We have the egocentric camera, and simply by asking the user to look at these posters, then it triggers the command. If the user looks at the center, we detect the poster. After detecting the poster, we start turning. We ask the user to say, is that an object you want? This is the poster. We show the poster on the screen of the tablet, and we say, is this the poster you want to go to? And then the user says yes, and then when it says yes, we start rotating the wheelchairs towards the poster until we reach there. We pick it up by the Connect camera. The Connect camera has a depth sensor, so after we pick it up, we match them. We make sure we're matching the same poster on both cameras. After we do that, we navigate to the point. We do the matching, then ransack, we remove the outliers. Then we make using homography, using homography, we remove the outliers, and then we navigate to the poster. This is more explanation on how do we pick up. So after we ask the user to pick up the objects on the wearable camera, we try to the object may be out of the let me show you in the video. So the object at the beginning, it may be out of the field of view of the Connect. So we want to start rotating the wheelchairs until we see it, and this will show now in the video. Until we see it, and then we start doing the matches of feature matches. And here's the example of the system run. Now, first is looking at this poster. And at this moment, it was the poster was showing on both cameras, so it was easy. It just drive through. The camera is mounted on the head, on the hand. And then at this time, the user looks at this poster and asks for to go to that poster, but it wasn't showing, so it started turning to this side. Why did it turn to this side? Because it keeps track of the last time you saw the QR marker. And if the last time you saw the QR marker was to the left of the camera, to the right of the camera, then I was turning it, would think the object you found is to the left. If the QR marker last seen was to the left side, then it will start turning to the right. This will save time on the navigation time. Here we also have a similar example where we allow integrated also the face detection and recognition. So here simply is we set in the system for target to was me in the system, and then it recognizes me and it keep turning until it finds the user, and it gets help from the egocentric camera or the user. So the user helped the robot find the target user by rotating and finding it in the scene. So it saves times on the wheelchairs, and this kind of collaboration between the system and the users allow for more efficiency. And sometimes it's not only efficiency what we're looking for, is also, I think, for many wheelchair users, having them in the loop and having some autonomy of their driving, it may be more preferable than just allowing autonomous navigation without their help. One more scenario on where we have a semi-nurse. If we're in the hospital and there's a nurse, we develop this tracking and detection and tracking system where a user could walk around and then the system will follow, autonomously will follow the user. Okay, now we come to a different part. We developed all these applications. We developed a way for the system to drive itself autonomously, a way for the system to be driven manually by the user, hands-free. And then we have all these semi-autonomous applications, such as the home navigation, where we ask semi-autonomous, where we ask for the route. And we have the other one where we help with the human guided and finding a human and finding the post. So now we want to look into it specifically the human navigation, the home navigation, where we used to pick a route. Why do we want to do that? We want to develop a way of learning how does the user, what does the user prefer, and then follow on that. So if the user prefers to take the left route, then next time we don't need to ask, we'll directly go to the left route. If we are not uncertain, if we are not certain, then we develop this uncertainty model to decide when to ask and when not to ask the user. Because if I ask the user today, I'm going to need to ask him the same question tomorrow, and so on and so forth. Now, it also applies that we don't need the system to always run on the same environment, the same maps. We actually have to try the system in different maps. So we trained it on one room, and then we tested another room. And we saw whether the system will pick up the user preference and follow on it. And we'll show the results later on. So why do we want to do that? We want to learn the user from user-based navigation, whether it was manual or it was autonomously driven or semi-autonomous. We learn from that, learn what's necessary to involve the user. This is the uncertainty model job. Is if you're certain, then you act on it and you drive autonomously. If you're not certain, then you ask the user to get involved and guide you to which way to go. Learn users' preferences in path selections or demonstration. So we also want to study here, is it possible to learn the user preferences or not? There was a lot of work, studies on suggest that people with mobility difficulty like to have control, which is something that we have to think of. It's not always more autonomy is preferred. Sometimes it may be less preferred. It depends on the person. So I think it's very important to develop these systems where we have multiple levels of autonomy, and especially when it's involved elderly or people with mobility difficulties. I think very important to give them both options to make them feel more in control, if that's what they prefer. Not necessarily that's what they want, but depends on preference of the person. Second is there was a lot of work in finding which path is more comfortable, which way of turning is more comfortable. Is the user always want to go to a straight route, or is the user always want to do a lot of turns? Is it, as a user, I would prefer to take the longer route if it was 10% less turns, or is 50% more turns? So this is all something sometimes it's hard to measure and put a criteria, but it's easier to just let the user try and learn all these preferences without asking too many questions. Okay, so that's bring us to another subject, which is if we think of learning path, if I have this scenario case where I have the start point and the end point, and if I want to go from the start to the end point, if I ask how many paths exist from the start to the end goal, the answer may vary. In one case, people will look at it and say, well, there's two routes. There's one route to the left and one route to the right. But if we actually want to make these routes, they're actually much more possible routes. You could go anywhere. You could go 1 centimeter to the right, and then you call it another path. So then we came to defining this and making sure what we mean by different path is what's usually people think of different path, not what's numerically written. So so we think of it as so there is the answer in mathematics. There's a homotopy class, and then it simply says if there is two paths that could be continuously there's a function that can take one path and continuously transfer it to the other, then they are belonging to the same homotopy class. If there wasn't, then they don't belong to the same homotopy class. So then we redefine this and we say, well, we only take the homotopically distinct path, and which is in this case will be only two routes. So any path around this part will be equivalent to the yellow one homotopically. They will be homotopically equivalent. And those two are homotopically distinct, but not actually, not the only two existing paths. And this goes more into the question, how about if we have this location here? Is the only path exist straight? How about if I want to take a turn here? It's going to be this way or the other way. It comes all sorts of different paths. But on homotopically speaking, it's only one homotopically distinct path exists. So we developed two ways for planners, two path planners. One will only get homotopically distinct path, and the other is a modified version of the A-star planner, where it gets us multiple paths, even though they are all homotopically the same, but it can get us multiple paths. And that allows us to learn more preferences of the user. The first one, the path that gets homotopically distinct path is based on the GBD planner, or generalized Bernoulli diagram, and which finds us only homotopically distinct path, and the other one based on the A-star algorithm. But the only difference between the iterative A-star planner and the A-star planner is that after finding every path, we block the area, and then we ask the planner to find us an alternative multiple times until it cannot find no more paths. To learn the preferences, we had to find a feature vector for each path. So we defined a set of features, and these 7 features, what we thought may be meaningful to the users. And one of these is we defined is the length of the path. Okay, how long is this path? Typically, people want shorter path to get to their distance. The second is narrow passage length. So how many narrow area I'm going to have to go through as a wheelchair user to get to my destination? Is it long narrow area or is it short narrow area? We thought maybe a lot of people want like narrow passages. The second is the average distance to obstacles. And then we defined obstacles. Say, well, static obstacles, dynamic obstacles is different. The average distance to obstacles, meaning how long will I be close to obstacles along the path? Along this side of the path of the route, I'll be close 1 meter. Along in the center, I'll be close 2 meters, the closest path to me. Or I will be 10 centimeters away, which increases the chances of accident for me. So we added this into the calibration because, again, people maybe want to be far from obstacles. They will may fear hitting these obstacles if they drive through certain routes. They will feel less secure or less safe, etc. And this is the average distance to obstacles, the minimum distance to obstacles, and then the sum of all turning angles. So we count the angles through the routes, and then we see how much turning happening, and then we calculate that. The sum of the turns that will have to be happening on the route are usually the less likely this route is preferable by users, but we put that as a fifth feature. And then we also thought of dynamic environments. How about if there is people in the scene? Maybe if there is obstacles, I don't mind getting close to obstacles, but I don't mind getting close to dynamic obstacles such as people or pets, etc. So put that into the equation, and the fifth is, and we added the average distance to people, and we added the minimum distance to people. I put that all into the equations, and this is how we learn, and this is how we learn paths. So we train a SVM model, a pairwise ranking model, which allows us to prefer, if giving set of routes, it tells us which route is better or which route is more preferable by the user. So this is how we train the model. We take in a scenario where the user, when we collected the data, if a user took a route 1, and then at the moment had 5 alternatives, then the user actually liked the number 1 path over the other 5s. So this is how we learn it. We map the 2 routes, the 1 route the user actually took, and the other 5 routes. And then this is built as 5 different feature representations that we can learn from. Of course, we labeled it with 1 as preferred, or minus 1 as less preferred. Now with that, we can get now how much prefer this path on the other path is something we used in the uncertainty model. So if I like this path more than all other paths, that means I should be certain I should take this path. I don't need to ask the user. However, if I find the top 2 paths that exist in my environment are very close in similarity and they're very close to user preferences, then I may ask the user. Unless I ask him multiple times, then this differences will get more separate in score, and I will get more certain next times. So this is simply how we get the uncertainty model to work with the user's experiences. So also to train this, we had to run experiments on a simulator as first, and then to collect more samples, we had to train on simulators. So we built these maps, and we asked the user to choose routes all over. Users start clicking on these routes, saying I want this, that, and avoiding certain routes. We tried them from different locations, different maps, and we recruited 2 subjects at first. We had 2 subjects and 36 scenarios, and they used to pick one of these routes showing on the map. What we found is, so on the y-axis, we represent how much of the time we ask the user to involve. So the uncertainty model tells me there is high number of similar routes. That's all of them are candidates. So I need the user to break the tie. There's 2 paths that's so likely to be picked by the user. User, please let me know which one would you take. When I ask the system more, I get lower accuracy. When I ask him less, I get lower accuracy. That means I'm only asking when I'm not very certain. So then the accuracy gets higher. And we did this for user 1 and user 2. And we found one of them is clearly easy to learn preferences. However, even the lowest part where we did the system decide, when we let the system decide 100% decisions, it was accuracy around 87 or 85. So still high. So it was easy to learn these 7 features preferences. So that was for the static environment where we did no people in the scene. However, when we added people to the scene, we noticed that's even much easier to recognize people preferences. It seemed like people, when there were people existing in the scene, we found that our users more, one of them was more social, one of them was less social, and then the antisocial one was more picking up routes that's farther from the system than closer to the system. Routes closer to people rather than routes far from the people. And here's a quick video onto uncertainty model, showing when to involve the system, when to involve the user, and when not to involve the user in the same home navigation scenario. It did not ask about the route. It picked the wider. It picked this wider and shorter path. However, when we ask the same question again, and there's people in the scene, even though people are not blocking the scene, the way, but because there are people in the scene, it picked the other routes. Even though it was longer and it was wider than this side. So we did also more experimentation, and this time, instead of asking the user to choose routes, we asked the user to execute this route. So they use the hands-free navigation method, and they drive into certain environments, and we record these trajectories. And let's say the user did this blue trajectories, we map it to its homotopically distinct path, and then we train on the homotopically distinct path. The same thing, we use the train pairwise ranking model on the same thing, and it produced similar results. We had more maps as well. This is the actual map drawn by our SLAM system. At this time, we had 14 subjects. We had more maps and more static and dynamic maps. So we have people in the scene, no people in the scene, and then still we had also higher accuracy here in the dynamic scene, the static scene, and then we combine them. How about if we done one model for both scenes? How would accuracy be? And then also we looked at something else here. Since we had data from simulator. We had data from these simulators, and we had data from real world examples. So then that allows us to try to look into, would the simulated data be enough or not? If we learn only on simulation, we'll be able to apply it on real data without having any real data access. This is very critical, and we found it still has a good accuracy. It was 78 for all users. But of course, it degrades from having real data for real scenarios, which is 86. But this was another something interesting to look at, because giving this data, if it was to train on, simulation, it would be much more easier and more efficient. Simulation could be distributed worldwide over the internet. We can get tons of data, unlike if we have to put people on the wheelchairs, ask them to drive around, so we learn from their experiences. Okay, in conclusion, the approach can learn preferences, and it also could work on actual environment or simulated. Learning from the simulated data also work. We've tried this to be trained on the environment, on the simulation, and then deployed directly on the real world data. And both it has shown, and the simulated and in the real world data, and it was evaluated on both. The last thing, and I think I have only 5 minutes, but it's very brief. So this is for system now my students are doing for their senior project. And this one targeting different types of people, not people with motor difficulties, but people with sight difficulties. So actually they don't have any motor difficulty, they can walk around. Their only problem is either their vision or the sight is blurred, or they have a complete blindness, so their vision is disturbed. So what is the target here? We want to let them use a wearable camera that's also mounted on a hat or a Google Glass. So any type of cameras that could be wearable, and then we allow the person wearing these glasses or this camera to see the environments and hear more about the environments, which will help them avoid obstacles. In safety, they will avoid obstacles. If they find obstacles in front of them, using object detection or recognition, we can recognize what object in front and ask them to avoid it. It may help them also with social interaction. We also use the facial expression recognition system, where allow the user to navigate better with others. So people with difficulty in sight, they can see what the others people in front of them are expressing in their faces. Also, we can improve their mobility with navigation guidelines. We can guide them to go right, go left, etc. We can increase their security, for instance, by using facial expression. Let's say you're in a subway or in a very dangerous area, and then this person is walking around and then seeing people with certain behavior right around them, maybe planning to steal something from them or attack them. Maybe this will give them some sense of safety and security, alert them earlier. Well, I can see a person looks very angry in front of me, maybe I should avoid, maybe I should leave the area. This all could alert the user and help them with their mobility. So how this is work is only one camera, wearable camera, connected to a laptop or a microcontroller. So let's say I carry my laptop in the backpack, and then I have the camera on the eyeglasses or a hat and my headphones or a speaker. I work in an indoor environment for now, and then walking around, I get these alerts telling me where to go when there is a bad situation. And if I'm talking to people, I want to hear how they express their feeling and how they are interacting with me. How do we design it? The design is very simple. The camera will pick up every object. All objects will be detected, and then it classify these objects. If the object is a human, then we go into face detection and recognition. If the object is something else, then we start to recognize and see their distances. And then if they're within 2 meters, then I want to know about them more. I want to know if the object is close, it's not close, where should I go, etc. And here's a small video. It's very new, project still didn't finish.
Is 30 centimeters away from you.
Quick. It allows them it allows the person to start seeing what's in front, allows them with distance, gives them distance. It's all through voice command, and this is supposed to be on headphones, so the user will get all this feedback while still navigating the environment. I don't want to take much of my time, so I'd like to thank my collaborators. Most of my collaborators at the time for the wheelchair used to be at Stevens. Now only one of them at Stevens, and then for the last part of the project is my students Nadia, Naif, and Amir at Saudi Electronic University. And last, I'd like to thank you all for listening, and thank you.
Thank you very much, Professor. We will have the Q&A session after the next talk.